This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your host, Radio Joe Hughes, and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day, wherever you're listening from, and welcome. It's IAQ Radio. This week, we're going to talk about using building science and the EPA Moisture Control Guide to improve indoor environmental quality. Hey, check out our YouTube channel when you get a chance. You can go to the IAQ Radio website, and there's a link there for YouTube. We've moved our podcasts over to Podbean, but you can still get them on TalkShoe. And, of course, we've got a Facebook page. Like our Facebook page, if you would. Let's start by thanking our marquee sponsors.
IAQ Radio marquee sponsors are John Don Products, where restoration and abatement contractors shop. Visit them at jondon.com. That's JONDON.com. Healthy Indoor Magazine, a free online digital magazine for industry professionals and consumers. Subscriptions are available at IAQ.net. Particles Plus, engineers and manufacturers feature rich particle counters, air quality monitoring, instrumentation, and vacuum pump technology. ParticlesPlus.com. Count on us. And now you can win a cool prize. It's time for the IAQ Radio Trivia question. Be the first to correctly answer. Simply email your answer to czlotnick@cs.com. Or if listening live, just text your answer from your computer. And now, here's the Z-Man with this week's IAQ Radio Trivia question.
Hello, everyone. Congratulations to Doug Conan, Aerotech Environmental, Dayton, Ohio, for being first to provide a definition for home performance as being a philosophy and a science based on the premise that homes should be safe, healthy, comfortable, durable, and efficient. The IQ Radio Trivia question for today, March 16, 2018, has been sponsored by Ideas, the solution chemistry company, creating unique solutions to odor removal, surface cleaning, and decontamination problems. Here is today's trivia question. Who were the three primary contributors to the EPA's moisture control guidance for building design, construction, and maintenance? Back to you, Joe.
Thanks, Cliff. We're going to talk a lot about that document today, and we're going to talk a lot about building science and EPA's moisture control guide and solving IEQ problems. Let's jump right into it, John. Let's start out with, let's go one more slide here. Cut right through that one. All right. So first, let's get some background here, and I want to go over some very important and excellent documents available for doing this for building science. Let's start with building science. I've used the Healthy Housing Reference Manual from the HUD and Department of Housing. We used a lot of information from the Building Science Corporation, Joe Lstiburek and Betsy Pettit's website. Really nice website with a lot of great information on it, buildingscience.com. And the up-and-coming one is the U.S. Department of Energy Building Technologies Program. We'll have some information from there as well. So those are kind of my three main background sources for the foundation we're going to set with respect to building science. Let's go to the next one. All right, and then we're going to go into the moisture control guidance for building design, construction, and maintenance from EPA. Excellent document. I just had to put together a little report, and while doing that, I used a lot of the information from this document, so we're going to walk you through that and kind of show you how to do that. All right, so when I first tell people who are hiring an indoor environmental professional, and I get these calls quite a bit. You know, I get people from around the country that call and they're looking for someone to help them with their building. I tell them these things. First, you need someone that's going to help you with building science, that understands building science. They don't have to be an expert, but they have to know enough about buildings and building science to help you solve your problem. They should also be focused on the root cause of your issue. So what's the reason for your odor? What's the reason for your moisture issue? What's the reason for the VOCs being elevated? Not what the numbers are so much, but what's the reason for it? What's behind it? Now, nothing wrong with some sampling and confirming things, but that's not the first thing they should look for. It shouldn't be immediately want to take a bunch of samples. Let's sit down, let's talk, let's review the issue, let's go through some blueprints if you've got them. Let's walk through the facility with the facility people or the homeowner, whomever it may be that you're working with, and let's try and get the background established before we even think about developing a hypothesis and then testing to try and prove or disprove that hypothesis. They also need to have a network of professionals they can reach out to. One of the projects we'll look at today, we had to use an HVAC cleaning company. We had to use a excavation company. We had to use a restoration contractor. So they need to have a good network of professionals they can help you with. And then one of the things I mentioned is look for IAQA membership. It's not a guarantee. The same with ACAC certification, not a guarantee, but it's a good start. And then most important, get references and call them. Just like you would with any other project. Make sure you are getting the information on the person that's coming in to do your building or your home. All right, so we had Joe Lstiburek on the show, and Joe, most of you are familiar with. He's kind of like the godfather of building science. And he told us that building science was a term used to describe the study of building enclosures and mechanical systems. He went on to say, or you could get more philosophical, and you could describe it as the technical side of architecture or the architectural side of engineering. It could also be considered the missing link between the architectural profession and the engineering profession. So the building scientists are the guys that have to make sure that the nice, beautiful looking plans and the well-engineered design work together to help us with have an environment that is healthy and is going to last for a long time and that is going to work. All right, so this is just a building enclosure. That's actually the world headquarters of IAQ Radio right there. And let's start with the background. How do buildings get damaged? Andy Osk, I should have put Andy in the announcement and put him up on this slide. We'll put it up before we post these. Andy Osk came out with a great article many years ago called HARM, H-A-R-M. And in that article, he discusses how heat, air, radiation, and moisture are the things that damage our buildings. And he does a good job of going through and explaining how heat. So let's take an example. Cliff is, I'm very familiar with. Cliff's the odor guru. Heat exacerbates odors sometimes. If you have blinds that are constantly getting heated, you may get some off-gassing from those blinds. When you heat volatile organic compounds in buildings, you can get more off-gassing. I'm sure, Cliff, you have some other examples, but I don't know if you want to go through them now or not.
No, we can go.
All right, next is air. I think this is one of the things we oftentimes leave out. We think about it when we think about things like stack effect, and stack effect is really important in buildings, but sometimes we don't think about the wind hitting on the side of a building. And of course, going back to last week's show with Nate Adams, we talked a lot about air leakage in homes and buildings, and that's a vital component to understanding building science and understanding how that building is operating. The next one is radiation. Another one a lot of people don't think much about, but radiation degrades building materials. So you've got to think about radiation. It also can add to the heat, etc. So you've got to look at HARM, H-A-R, and the one that most people look at on a regular basis is moisture, of course. That's the big one. All right. So the I-beam program, the interactive, the Indoor Air Quality Building Education and Assessment Model is I-beam. I'll put the slide in here a little later. There's a cover of I-beam. If you don't have a copy of I-beam, you need to get one. They don't make the CD anymore where you can get it and run it on your computer, but you can download everything from the EPA website on the I-beam. So just type into your Google search or whatever search you use, I-BEM, Indoor Air Quality Building Education and Assessment Model. Great document. This is where we're going to go now. All right. So I take this from, actually, I don't know where Mike got it from. Mike McGuinness he really emphasizes the 4 Ps of IAQ. I-beam has it set up a little different. So let's go through that right now. The first P is people. we don't, if you don't have people in the building, well, what's the problem? We've got to have people, and we've got to use the people and talk to the people to get an idea of what exactly is going on in that building. The second P is pressure. Oftentimes that can be affected by the HVAC system, but it can also be wind, it can be stack effect, etc. Then we have pathways. We have to have pathways, and the diagram up on your screen right now is a great one showing some pathways for a typical indoor contaminant, radon. And then we have some kind of pollutant. In the case in the graphic there, it's going to be the radon. So the radon has a pathway through where the sump pump is, or through a crack in the slab, up into the home. It's because of the pressurization. Typically there's stack effect, and the radon rises up into the home, and then we have the people. So if we put all those connections together, we have the fifth problem, which is the fifth P, which is problems. All right. So this is just an illustration of air barrier issues. This again comes from an article by John Straub. Used to be with Building Science Corporation. Now their company's Building Science Labs, I believe it is, up in Toronto area. Great folks. They show this stack effect in the winter, and then the opposite occurring in the summer. I think sometimes we forget that the opposite can occur. So stack effect is a huge issue when it comes to the pressurizations in the building. And then there's wind. We mentioned this a little bit earlier, but wind on the windward side of the house has a positive pressure, and it may have a negative pressure on the leeward side. So I think a lot of times we think of buildings and homes as having a negative pressure or a positive pressure. They have both. They may have a negative pressure at the bottom and a positive pressure at the top. They may have a negative pressure on one side and a positive pressure on the other side of the home. So we've got to keep that in mind when we're doing these investigations. And here's my other slide on the 4 Ps. You've got to have the people, the pollutant, and they need to be connected through pressurization and pathway. So if we go back to that radon slide, go back one, maybe 2 more. There we go. So we've got the 4 Ps here. If we've got people in that building, there's a pollutant that's trying to make its way into the building. We have 2 ways of stopping that. One is through pressurization, which is going to be difficult. We could try and positively pressurize the basement, but the better way would be to work on our pathways. And in this case, we'd use 2 pathways. One would be sealing the pathways coming up into the basement. The second would be providing a pathway for that radon to go up and out of the home. So a radon mitigation system is a great example. The other thing I want to point out on this slide is the I-beam document doesn't use the 4 Ps. They use occupants, HVAC, pathways, and sources. So any of you that may be taking the ACAC CIE exam, or I might be on the certified microbial consultant as well, rather than using the 4 Ps, you want to use the I-beams, occupants, HVAC, pathways, and sources. Those 4 together lead to problems. All right. So here's another great slide from I-beam. I've got 2 of them that illustrates this whole idea of people, pollutant, pathway, pressurization. You can see we've got the people in there. We've got 3 separate zones. One is positively pressurized on the left. That's going to be an office area. The second one might be another office area. We want those to be positively pressurized compared to the lab area where the guy's doing some work under a fume hood of some type. So it illustrates the 4 Ps real nicely. Now, when those get confused or thrown off, this is what we could end up with. And this comes on the I-beam as well. Go ahead. So here, now we've got essentially a negative pressure in all 3 of those areas, and we're going to draw fumes back into the office spaces where we don't want them. So we want to do what they call pressure mapping, and you want to go into the building and you want to look at the pressurizations between different rooms, between different floors, between different, the inside and the outside. These can all help you in figuring out through the 4 Ps whether there's an indoor air quality problem. All right, another key topic that the Joe Lstiburek really started talking about this 20 years ago, maybe longer now. And it's something that I notice quite a bit because I travel around the country a lot. And it's the climate zone that you're in. And this is a real basic climate zone map. There's also good climate zone maps on the Department of Energy website. But you can see what we've got here are the southeast of the United States primarily is going to be a hot, humid climate. The green part, kind of in the middle where you've got the North Carolina, South Carolina, Virginia, that's a mixed humid climate. Then when you move up into where we're at in Pennsylvania and all through North Dakota, Nebraska, or well, South Dakota, Nebraska, Iowa, you've got the cold climate. If we go out to Southern California, parts of Texas, the top of Mexico, New Mexico, Arizona, we've got a hot, dry climate. And then, of course, up in Canada, we've got a very cold climate. As some will say, you've got two seasons, this winter and last winter. But those are the climate zones. Now, I think the first thing I would look at with the climate zone differences, and what I notice is the different types of foundations that buildings are built on based on the type of climate. Now, it's not exclusive. So, for instance, in that hot, humid climate down in Florida and the Gulf Coast, you're commonly going to see slab-on-grade type construction. So they've got a slab that goes on top of some dirt. Hopefully, they've got a vapor barrier under there. Hopefully, they put some stone under there so there's good drainage away from the building. But that's the first kind of thing you want to think about. What type of construction do I have? Commonly, we'll also find in the mixed humid climate a lot of crawl spaces, and crawl spaces have their own issues. So we want to look at what type of building do I have? Now, that doesn't mean you won't find slabs. You will find slabs in all these areas. You'll find basements in all these areas, but more commonly, you'll find a lot of crawl space type construction in that mixed humid climate. In the cold climate, we're commonly going to see basements, and we're going to see one here in a moment. Hot, dry climate, more common that you would see, again, a slab type construction. And again, up in the very cold climate, more common you'd see basements, although a lot of builders today are going to slab on grade construction wherever they're at, or they're going to condition crawl spaces where they have a crawl space, but it's conditioned in a way that's similar, that keeps the temperature, the humidity, etc., similar to the rest of the building. All right, we also have to think about what kind of precipitation we have in that area. And I want to point out on Pennsylvania, if those of you that can pick out Pennsylvania there on the map, one of the projects we're going to talk about today is right where that bunch of blue goes up into Pennsylvania there. We get a good bit of snow and rain in that area. To the right, we get more snow because we're in the Allegheny Mountains. And one of the projects we're going to talk about today is in the Allegheny Mountains, and there's a lot of snow, ice damming, and other issues. Now, if you got a very dry climate, you may want to, again, think about that when you're going out and looking at your job. The thing with some of these dry climates is you've got to watch because it's dry most of the time, but when they do get hit, they can get pounded with rain. So they've got to have good ways to drain that rain away from their buildings. All right. So I first want to point out a really great article. If you get a chance, go to Joe Lstiburek's website, buildingscience.com. And it's called, Why Do We Have So Many Problems with Buildings Today? And he goes over 5 reasons we have more problems today than what we've had in the past. And a lot of this is related to moisture issues. I think most of us in our practices will probably get at least 50% or maybe up to 80 or 90% of our projects might well be moisture related. Of course, the restoration guys are commonly doing moisture related projects, maybe as much as 90 to 100% of the time. But anyway, Joe says because of these 5 things, we have more problems today. Increased thermal resistance, a change in the permeability of linings, water and mold sensitivity of building materials, the ability of the building enclosure to store and redistribute moisture, and complex 3-dimensional airflow networks that inadvertently couple the building enclosure to the breathing zone of the occupied space via the mechanical system. So let's look at each one real quick. I'm not going to spend a lot of time on this one because it's something you should read in more detail. We're going to show you some examples, though, in one of the projects coming up of just about each of these 5 reasons. The first one is the increased thermal resistance. So we now have better insulation, better thermal resistance between the inside and the outside. That's going to change things. In the old days when we had buildings that didn't have any insulation, they could get wet. you could let that water could get into your wall cavity, but when you heat the building, which was pretty common in a lot of these northern climates in particular, the water would dry out. But when you've got insulation in there, it doesn't dry as easily. So we've got to think about the changes in thermal resistance. Then we look at the permeability of linings we put on the inside and the outside of the building enclosure. We see things like wallpaper. Joe shows an example of wallpaper issues. An example on the left would be using a polyethylene vapor barrier on the interior of walls. Now, this used to actually be code in some places, but the code has gotten much better. They don't use that as often, but you'll still find it in buildings. And in fact, one of our case studies we're going to show, there was a polyethylene vapor barrier put up on the walls in the basement behind the, it was like, we'll just use drywall. And the sensitivity of building materials. Newer building materials can be more sensitive to moisture and mold issues. So where we used to have plaster, we now have drywall. Where we used to have a drywall or plaster ceiling, we may now have ceiling tile, which is very easy to grow. You know, it's not very resistant to mold unless you buy a type that is resistant. Where we used to have a 12 by 2 by 12 floor joist, we now have something like what you see in the photo. It's what some people refer to as was wood. At one time it was wood. Now it's a bunch of chips of wood all glued together, sandwiched in between a couple of 1 by 2s. And then the ability of the building enclosure to store and redistribute moisture is a big problem for us in buildings today. On the left, we've got an old mass wall construction building that could get really wet. The rain hits it. It might soak into it, but it will store and redistribute that water and allow it to dry out. Now, the thing you don't want to do is change that without thinking about what you're going to do to that ability to redistribute the water and dry out. So putting insulation on the inside of this building becomes something that has to be designed properly. The building on the right, go back one for a second, John. We've got basically no place for water to be stored, redistributed, or to dry out. It's a very difficult issue. Now, they do have the newer type of, not newer anymore, it's probably 20 years or more now. They've been using the fiberglass coated exterior sheathing, which is nice. You know, it doesn't mold up, but we still have very little room for water, very little ability for the water to be stored, redistributed, and then to dry back out. You're probably going to have drywall on the inside of those walls. So you've got a metal channel, probably some kind of insulation. Fiberglass would be common, and that's not going to store and redistribute water. You've got steel studs, not going to be able to store and redistribute the water. You've got drywall on the inside, same thing. So our buildings are more susceptible to the issues today. All right, so again, we want to think about the 4 Ps: people, pollutant, pathway, pressurization. Let's look at the next slide. Here's an example. This is one I love from, I can't remember exactly where this one's from at the moment, but I'll pull it up later. And I know Joe Lstiburek talks a lot about this issue. What you've got is a, pretty standard construction, typical 2-story, let's say, commercial building, where you've got going from the outside in, you've got a brick veneer. Hopefully you've got a gap there between the brick veneer and the building paper. Hopefully you have building paper. Then you're going to have your exterior sheathing behind your building paper. Then you're going to have your metal stud wall and some kind of cavity insulation. And commonly they'll also put up in this little section where your I-beam is. Can you point to that, John? Right in here. They're going to stuff some insulation in there a lot of times, right in there. It may or may not be a good air barrier. Most of the time they just stuff a little fiberglass in there, which is a horrible air barrier. And so you can see what happens if you've got in that building a suspended ceiling on the inside with interior gypsum, and then you've got a return air plenum above your ceiling. So your ceiling between your suspended ceiling and the floor above is going to be negatively pressurized. It's a big return duct. So it's supposed to be sucking air from a grill in the room up into that return air plenum, going back to your air handling unit. But what we don't think about sometimes is it's not just, there's no traffic cop there saying the only air that can come up here and the only air that can be redistributed through the building is the stuff that's in the room. It's going to also suck from the wall cavity. It's going to suck from between the floors. And that's where we get a lot of issues. We've got, contaminants in there like pesticides, or you might have moisture. You might have old lead paint. You could have there might be some old asbestos siding behind there. So again, the 4 Ps, think about people, pollutant, pressure, pathway. If I've got a negative pressure above that suspended ceiling, there's a chance I could be pulling air from my wall cavity. How do I stop that? I've got to stop either the pathway or the pressurization. So I could maybe put a duct up in there as opposed to having a return air plenum. Or I could go up in there and try and seal the pathways, which is probably a good idea anyway. But you can kind of get the idea of how we play with the 4 Ps to help solve these problems. Okay. In the Andy Osk article, Harm, Heat, Air, Radiation, and Moisture, he talks about how HVAC and building science are inextricably linked. Heating, ventilation, and air conditioning. The natural laws of physics and thermodynamics have to govern our inspection process. Now, we don't have time to go into all that today, but if you don't understand thermodynamics, you've got to look at the laws of physics and the laws of thermodynamics and get a better understanding of those so that it'll help you with understanding building science. These are inextricably linked, the HVAC and the building enclosure. The other thing we want to talk about very briefly, we won't have time to get into a lot of detail, is ventilation. There's a lot of people talking today, and it's true, we want to build our buildings tight and we want to ventilate them right. But oftentimes that's easier said than done, particularly when you get situations like this where we've got fume hoods in a science building. These can cause all kinds of pressure issues, and in one of our case studies, we'll show you some examples of the types of issues that can be caused. All right, so now we're going to move, see what time we got, into the moisture control guide. Excellent document, just fantastic. I mean, I don't even have it in here, but start with the introduction. In the introduction, they go over the reason why moisture control is so important, and they talk about the studies that have been done over the years, the health-related issues, and it's current. The moisture control guide is only, 3 years old now? What's the date on there, John? The end of 2013, I think it was. So you're looking at January, basically, of 2014 before anybody had it. Here we are in January. So that's about 4 years old, let's say. And I don't think it gets out enough, and I don't think enough people are really using it the way it could be used. So I wanted to really emphasize that document in this show. Let's go to the next slide. All right. The 2 ways that water vapor enters our buildings, or the 2 main mechanisms, are going to be vapor diffusion and air infiltration. And then, of course, liquid water. Let's just leave it at liquid water and then water that's in the vapor form. Those are going to be our 2 most common ways. There are other potential ways for moisture to enter the building, but let's go to the next slide where we've got a little more detail. Here's the basics of water behavior as discussed in the EPA Moisture Control Guide. And you can see, water runs, of course, through pipes and vessels. It runs downhill. It can wick upward. It runs along the bottom and sides of materials. Water vapor in the air goes where the air goes. So again, the 4 Ps, people, pollutant, pressure, pathway. It goes where the air goes. So we have to understand those pressures and we have to understand those pathways. Water vapor can, though, migrate through materials by diffusion. But in my experience and most of the people I work with, that's much less common than water vapor in the air going through leaky building enclosures. So you're going to get a lot more water in the air than you're going to get diffusing through materials. Water evaporates from liquid water on surfaces becoming a water vapor, and water vapor condenses on a surface becoming a liquid. And then water vapor is adsorbed onto surfaces. So these are the key points of water behavior per the EPA Moisture Control Guide. Okay, so I think at this point would be a good time to break for halftime. Cliff, any thoughts? Well, I know Cliff has an announcement, an important announcement, so let's turn it over to the Z-Man.
Thanks, Joe. I'm very saddened to share that Paul A. Lorenzi, Vice President of Sales and Marketing of the Delmhorst Instrument Company, passed away in his home in Montville, New Jersey on Sunday, March 11th, 2018, following a long struggle with anxiety and depression. Paul was an integral part of the management team at Delmhorst, a pioneering moisture detection and measurement firm. He joined the family business in 1990 and took on various roles, culminating in his leadership of the sales and marketing team as vice president. He believed in the Delmhorst brand and was tireless in his efforts to connect with customers and make Delmhorst the company it is today. I was a customer of Delmhorst long before I met Paul. He was interviewed on IAQ Radio episode 215 on July 29th, 2011. He was knowledgeable, kind, and an all-around good guy. Donations in Paul's memory may be made to the Trevor Project or the American Foundation for Suicide Prevention. Thank you, and back to you, Joe.
John, before we go to halftime, I want to mention to listeners, that was just an excellent show. Paul did a great job of discussing using moisture meters. It wasn't, just a sales pitch at all. I mean, we don't really do that. We try to avoid that here. But he talked about the pros and cons of different types of moisture meters. He went over some of the things that will affect your readings on moisture meters. He did a great job. We're going to put a link to that in the blog, but you can always just go to the IAQ Radio website, scroll down on the right-hand side. There's a search box. Type in Lorenzi, Laurenzi, and you'll find Paul's show. Let's go to halftime, John.
IAQ Radio would like to thank our association sponsors. The Indoor Air Quality Association, a nonprofit multidisciplinary organization dedicated to promoting the exchange of indoor environmental information through education and research. Visit them at iaqa.org. Gray Wolf Sensing Solutions, who use advanced sensor software technology and embedded computers to provide superior environmental test instrumentation. Visit them, wolfsense.com. IAQ marquee sponsors are John Don Products, where restoration and abatement contractors shop. Visit them at johndon.com. That's JONDON.com. Healthy Indoor Magazine, a free online digital magazine for industry professionals and consumers. Subscriptions are available at IAQ.net. Particles Plus, engineers and manufacturers feature rich particle counters, air quality monitoring, instrumentation, and vacuum pump technology. ParticlesPlus.com. Count on us.
All right, thanks. We're back for the second half of our show today, talking about building science and the EPA Moisture Control Guide and how to use it to solve IAQ problems. Let's go to this. Drain the rain. I love this one. I think it was Joe Lstiburek I first heard this from, and maybe you've all, heard this somewhere along the way, but drain the rain from the plane down and away from the building onto your neighbor's property. That's my version anyway. I don't know what his version is, but it's pretty close. So one of the things I love about this moisture control guide is the graphics. and the details that they have packed into this document. They're ours. We paid for them. Use them. I just put this out with a buddy of mine had a project that we're going to talk about here in a minute, but this was a great diagram for him to include in the report so that he could show them, look, this home should have a typical 8-inch drop at the foundation, then a 5% minimum grade for the first 10 feet, 2% minimum grade on lawn areas, etc. So it's a great way to show people from a cognizant authority, from EPA's Moisture Control Guide, this is the slope you should have. Here's the slope you do have. How do we get as close to the slope you should have as we can? And we don't just want to drain the water from the land around us. We want to drain the rain from the building itself. So we need to drain the roof properly. We need to drain any dormers properly. We need to flash windows properly. We need to have proper building paper on the building. And you can see a little diagram on how that works. We need to drain porches. We need to drain doors. We need to drain all around our foundation. We'll talk more about that in a moment. By the way, stay right there for just a minute, John. On the home that we're going to look at, they do have a really nice drain system similar to what you're seeing here, only they had 3 feet of crushed stone underneath this home and several additional drainage culverts in the back of the home because it's built right next to a hillside. So they had everything there, but one of the big problems we all find is they weren't maintained. There was actually a way to clean and to push, and to open up and get into the whole drainage system and clean it out. And hadn't been done. 22 years. The home was there for 22 years. Not once, I don't believe. I mean, I could be mistaken, but from the way it looked, it hadn't ever been cleaned. That alone may have been enough to stop some of the moisture issues. Now, typically what we find is a combination of things lead to a tipping point, or you find a job that's pretty simple. You got a broken pipe, like we had a broken toilet. Well, the broken toilet was pretty easy to figure out. Followed the water path, the migration of the water. We dried it out quick enough. It actually happened while Danny was still on the job. But anyway, let's go to the next one.
Joe, how would they maintain the drainage system?
They actually had, it's a good question, Cliff. In this case, all they needed to do is pull the grates, gather up all the leaves and branches and all that had gone into the grates, and then those were actually tied together with the downspouts that there was a place for downspouts, even though there aren't any. I'll go into that in just a moment. And those were also tied into the French drain system. So they were able to actually, in this case, just use a hose to clean it out. In some cases, they might have to use something like the Roto-Rooter, but in this case, it wasn't that bad. So most of the problem was at the grates, which were collecting all the water coming off a very big hillside. This is at a ski resort, so there's a large hillside on the back side and a ton of water coming down. And if you don't stop that first avalanche of water, it's kind of tough. You can have the best building enclosure in the world, but if you don't drain that rain around that building and away from that building, it's going to get overwhelmed. All right, so let's talk a little more about the moisture control guide here, because I think they do a really nice job here of going over what they call control layers. Now, in the past, I'm sure most of you have heard people talk about, there's a vapor barrier, there's a thermal barrier, there's a rain barrier, etc. We're going to use the EPA's way of, and this is from Lew Harriman, Terry Brennan. They wrote the EPA Moisture Control Guide. Great guys. Go back and check out those shows. We'll put them in the blog. We actually had them talking about the Moisture Control Guide. They went into a lot about how long it took to develop it. It was over 3 administrations, if I'm not mistaken, and how they put it together, and then some of their key points from the document. I'm going to go in a little more detail on the details in the document, because now we have the ability with IAQ Radio Plus to do that. So we've got a rainwater control layer, an insulation layer, and an air barrier. You notice they don't have the term vapor barrier in there anymore. I think that was confusing for people because a lot of times vapor barriers were not necessarily intentionally put in, but we still want to think about where there might be vapor barriers, and we'll talk about that as we go along. All right, so here's a great detail from the EPA Moisture Control Guide. This is for a slab on grade, but it's pretty similar for what you would find for other types of construction. It's a monolithic slab, so it's poured. The foundation you can see is over on the, can I use mine? They don't see mine, right in here, John. So we've got the footer and the foundation are kind of all one pour right here. We've got a granular drainage pad with coarse gravel, no fines. Then we've got a polyethylene vapor barrier in direct contact with the slab. If you're going to have a polyethylene vapor barrier anywhere in your building, this is the place to have it. And you can see that vapor barrier comes up on the exterior of the foundation, and then we've got the proper slope away from the home. We've got proper drainage for our downspouts to carry the rainwater, and they have details down below in this. I don't have them on this graphic showing you or writing out in a bullet point form how to put this together. It's perfect. You've got a client with a slab related issue, slap it in your report, give it to them, discuss what you find they actually have, and then discuss how you're going to do what you can do to get it as close to the way it should be today. All right, here's an example of a basement type construction, and this is what we're going to be seeing in a moment. And you can see we've got very similar kind of details. We've got the coarse gravel again down below. We've also got the gravel around our drain line here. We've got our, can you follow me along here, Joe? We've got our footer, our foundation wall, and then we've got our damp proofing and our capillary break. That's this blue line coming down, and it goes between the footer and the foundation wall. Then we've got our concrete foundation wall. Of course, we have a free draining backfill here on the project we'll be looking at. We're actually backfilling all the way to the top with just a little bit of river rock on top of that. A sloped topsoil cap. Keep it below the flashing at the bottom of your brick. And we've got a proper gap between our brick and our exterior sheathing. On the inside, we've got a foam board insulation. So it could be like an XPS, 1 inch, 2 inch, depends on what they tell you in the document is you have to do the calculation they have in the document to determine the amount of R value you need. Then they've got a studded wall with fiberglass insulation, and then a mold resistant gypsum board, no vapor barrier. Don't put the plastic in here like people used to do in the past, and like we found on the project we're going to look at here in a moment. We can see also they've got a polyethylene film underneath their slab, very common type of construction today in new construction. You don't see this very often in construction that's more than 15, 20 years old. So again, take the detail, take and figure out what you've got and try and get as close to the today's preferred detail as you can. All right, this is just another example of a great diagram. We're not going to have time to go through this one, but it's again another a wall section and how to put together a wall. So there's probably 50 or 75 great details in this document. Here's another area we find a lot of problems, and a lot of building owners kind of look at you with this look like, what are you talking about, when we ask them or discuss with them the flashing on their windows and the proper details on flashing of windows. This is the proper detail today for flashing of windows. In my experience, in a home older than 10 years, you almost never find this. Even in new construction today, you're commonly going to find some of these elements are missing. So for instance, one of the ones is the closure strip that flashes to the self-adhered membrane over here. Here's your your flashing. Here's your self-adhered membrane. Okay, it's another similar kind of. It's a flashing essentially, and then they've got another pan flashing over top of that. All right, but this is the way it should be done. Now, this is what I would call the belt and suspenders, Cliff. You know, it's kind of a little more than you're going to commonly find, but hey, if you want to be certain those windows don't leak and don't get down behind your exterior siding, well, you want to make sure that it's done right. This is the way you do it.
Well, they figure out how to do it right because they've tried and found all these ways to do it wrong, right?
We sure have. We sure have. I mean, my son does construction up here at Indian Lake at the world headquarters, and it's just amazing the garbage that was built back in the day. I mean, some of it's great stuff. Don't get me wrong, but there's some really bad construction out there from 40, 50 years ago. They were just thrown up as kind of like, summer places, and they're not ready for this winter that we have. We have a pretty rough winter up here on the mountain. You get ice damming, you get a lot of wind, you get a ton of snow, it melts, it freezes, etc. So they're just not ready for that, and they're nowhere near this type of construction. And it's tough for people to wrap around their mind. Wait a minute, I bought this home for $400,000 or $500,000. You mean to tell me it doesn't have all this stuff? No. It doesn't have half of that stuff. It doesn't have, I'll guarantee you, there's not one up on this lake that has that flashing detail on their windows. Even the newest ones probably don't have that flashing detail. So it's a tough thing for building owners to swallow. All right, so this is a little different. Let's skip this one, John. That's not from the Moisture Control Guide. The next thing I want to talk about now, this is with respect to solving problems. The Moisture Control Guide has an Appendix A they call the Penn Test. Now, many of you are probably familiar with the Penn Test, so I'm not going to spend a lot of time on it just for people that are new. This is where we're going to trace the rainwater protection layer, the insulation layer, and the air barrier. And sometimes you have to trace this in your mind. You don't always have a detail that shows you that wall section, that shows you that basement foundation, the way it was built. So sometimes you've got to open things up. You've got to put holes in things. You've got to dig holes. You've got to look at things in a way that sometimes building owners are a little hesitant about. But the only way you're going to figure it out for certain is by actually putting some holes in things. So what EPA recommends you do is take the detail, and and on this particular one, it's the rainwater control layer. And you should be able to draw a line, John, from around this rainwater control layer and trace it without any breaks in that control layer. And basically, you're not going to be able to do this typically with a detail. You won't have one for an existing building that has that kind of detail. You may, and in fact, sometimes on commercial buildings, you will have this. Most of the time on residential, you won't find this. But you should be able to trace the rainwater control layer so there's no breaks. That's the easy one. I think everyone understands if you've got a break in your rainwater control layer, you've got a problem. I mean, if you can't keep the liquid rainwater out of your house, as Joe said on our show, you might as well give up. The next one is the insulation layer. Now, this is a really good one and a good detail here. This is more of a commercial building, single story. You've got to trace the insulation again, and you can see we're going to trace it along the rooftop, and then we're going to come down. And right in here, oftentimes in this area where you've got I-beams or other types of structural elements, it's difficult to insulate properly. So it's a good place to look for a lack of insulation. Now, why would that cause moisture? I think most of our listeners know that where we have cold spots, we can have moisture problems. We get condensation, we get moisture problems. So we're looking for lack of insulation because we're going to have a difference between the inside and the outside, whether you're in the south or in the north. Doesn't really matter. You just flip it around, basically. You've got a cold spot, and that cold spot can be where you have condensation. You get condensation, you have moisture, you can get mold. And then the next one is to trace our air barrier. And this is one I find a lot, air barriers. Go back here, air barrier. Especially, again, in that same area, we rarely get a good air barrier right in here. A lot of times, you're going to have somebody stuff some fiberglass in there. And if you pull it out and look at the fiberglass, it's going to be black. The reason it's black is it's been acting as a filter. The air that's been pulling through there, the particulate in that air is being captured on that fiberglass. But a lot of the vapor is going right through and into your building. So again, we have to look at the 4 Ps. Is this a windward side? Do we have stack effect? So is the mechanical system set up in a way where you've got a plenum? Look for your negative pressures and where you might be pulling air in to your building that is not conditioned. It's not dehumidified, especially if you're in some of these mixed humid and hot humid climates. But we're finding that more and more here right above the Mason-Dixon line. Mason-Dixon line's at the bottom of Pennsylvania here. And what I'm finding is a lot more problems these days with air barrier issues because we're getting more hotter, more humid summers, and people are finding more problems in their buildings, especially in their crawl spaces, than they've had in the past. It gets hotter. What do people do? Add air conditioning. We put air conditioning in. We don't think about the fact that we're creating problems with maybe all 3 of these issues, not so much the moisture control barrier, but certainly the air barrier and the thermal barrier have to be carefully thought out before you just throw in an air conditioner. All right, so let's get to our case study. Nice home up on the mountain, ski resort. Nice home. I can't say who it is or anything like that, but I just want to give you some idea of some of the issues. This is this time of the year we get a lot of this ice damming. This is actually not really bad. It's not too bad at all. Notice no gutters. No gutters, no downspouts. Why is that? Well, upper end homes, $1 million homes, there's a
aesthetics.
They're not allowed. They have an agreement with the owners association. They're not allowed to put gutters and downspouts. The other reason is gutters and downspouts get tore up by this ice and snow. But there are times when we have to try and divert that water away from sensitive areas of the building, and we'll use things like roof diverters. But if you also notice up here in this corner, right here, John, there's no kick-out flashing. So there's no way to kick that water out away from just running down along the side of this building, hitting this window where there may or may not be proper flashing. The water gets behind the siding, then it drops to the bottom along the paper, and at the bottom it's stuck because there's caulking there instead of flashing. We had multiple issues. Common. It's generally not just one thing. So no gutters or downspouts. Not allowed in this case. Drain the rain from the plane down and away from the building. The slope was going toward the building in some cases. Had to clean the drains out. Good drainage system built, excellent drainage system built, actually. I was shocked when we dug it all up, tried to figure out what was going on. The foundation and the footer were doing their job. They were draining water away from the building. It was, like I said, on 3 or 4 feet of crushed stone. Really nice setup, well done. But you don't maintain it, you're going to have problems. No flashing at the stone siding interface. We'll show you what I mean by that in a moment. That's going to be our major issue on this particular project. We had a plastic vapor barrier over, let me describe the basement. Beautiful, bar, game room, fireplace, the whole 9 yards, a couple of bedrooms, exercise room, big place. But all the exterior walls in the basement had spray foam on them, actually, closed cell spray foam, unevenly applied, unfortunately. You'll see some examples here. And then on top of the spray foam, they had the 2x4 studs with open face fiberglass, which was good, just like we saw in the diagram from EPA, but then they put a plastic vapor barrier over top of that. Now, in this case, I don't think it did that much. I don't think it caused that much damage, but we'll talk about that when we get to that section. The other issue we found on this one, which is kind of rare, I don't see it that often, but there's some below slab ductwork. And I'm sure many of our listeners are familiar with this, especially if you live in the north, where they actually put the ductwork for the mechanical system underneath the slab. We'll show you that. In this case, though, it was actually in pretty decent shape, which is not real common. A lot of times those below slab ductwork actually need to be abandoned. They're so bad. We had ice dams, which I showed you. We had a lot of bound water in the construction, which I'll show you. And while there, Danny had a toilet break on them, which flooded an area, and a sprinkler break. So you can see we had a lot of issues on this one. All right. Here's an example of draining the rain from the plane down and away from the building. Right at the front entrance, you've got stone that is sinking toward the home. Not a good thing. To the right, you can see the green on the stone. What is that from? Well, that's moisture. Moisture is probably getting behind that stone, running down, all the way down to the top of the foundation wall. It's a problem. And a lot of that came from ice damming, I'm sure. But again, no kick-out flashing in that area. And the roof diverter, there is a roof diverter which pushes the water away from that intersection a little bit, but it gets clogged with leaves and so on and doesn't always do the job. Next. So in the back of the home, we've got similar setup. We've got stone, and then we've got, well, let's start at the bottom. You've got a footer, concrete footer. You've got 12-inch cinder block that they filled the cells in. They damp-proofed nicely. They put 4 inches of stone underneath. All well done. All working really well. Then you've got a brick ledge, which is actually 2 layers below where we're drilling. Okay, so there's 2 layers. There's a brick ledge, and that brick ledge, they put there was an 8-inch block of cinder block. Then they put a 4-inch block on the outside because instead of running the brick below grade, they probably had a problem with the grade issue here. Instead of running brick, they put an 8-inch block and a 4-inch block, and they didn't fill in these holes on this 8-inch block. So when we drilled a hole in it, which is one of the ways you try and find out these issues, you got to open things up. You got to dig a hole. We dug a hole all the way down to the foundation or to the footer. We looked at the footer. It was working properly. We ran water down there. It was draining great. We made sure that the drain line there was open. You can see they actually have a place to put a downspout, but they never did put the downspout in. They may in the future. We'll see. So we drill a hole, and on the right you can see what happened. It looked like someone was going to the bathroom right there. The water just came spurting out, like they turned the faucet on. It just came spurting out of the cell in that brick or in that cinder block. So you can't see it real well, but if you look at the top ledge, there is no flashing between the siding and the brick ledge here. And there needs to be flashing there. That's a missing detail on this particular project. Caulking won't do it. It's going to get in above, it's going to come down, and the caulking's actually causing a problem to some degree because it's holding that water in, and then it's going down behind the brick into the top of the cinder block. Not a good thing. The way it should have been done is this detail right here. Oh, there you go. So we should have had the flashing on top of that stone ledge, up underneath my house wrap, and underneath my exterior siding or exterior cladding, siding in this case, wood siding. And then I've got my interior or my exterior sheathing here. So we're missing this detail on this particular home, and that caused what we're going to see next. Water got behind, got into those brick cells, into the cinder block cells, came down behind the insulation. You can see the insulation there, and ran all the way down to the floor. Now, a lot of people would look at this and they would think, you've got a foundation issue here. This is not a foundation issue. We verified that. The foundation and the footer are working fine. The problem is water getting in, well, the very top row of the foundation, and the flashing and the other multiple issues. So this water ran down behind the closed cell foam. In this area, it looks like it's maybe a different type of foam, sort of like a styrofoam. They had actual closed cell in other areas. Ran down behind, hit the studs at the bottom, rotted the studs, elevated the humidity in the whole basement to the point where we had mold on contents, mold behind the drywall, mold behind the paneling they had in some areas, etc. Very common problem. Here you can see when we take off the foam, when you remove that sprayed on foam, there was moisture behind it. So there was condensation behind it. That's the water trying to work its way down, and or to some degree the temperature differential and the fact that we had a hole dug outside causing some of that condensation. But this foam was applied right, but above it was a problem. So the moisture is getting down below it. And here again is the way it should have been done. They were very close to this. The problem being they didn't have the flashing. In this case, we've just got a brick exterior, right? And in this, on the case study we're looking at, we've got here, instead of a poured wall, we've got cinder block, and then we've got holes in the cells of the block up here, and no flashing here, and we've got that siding up here. Let's go to the next one, John. All right. What time do I have, everybody? Okay, so we're going to have to look at this next case study at a later date, but I think we've got through some very good ones. This is an excellent, another commercial building case study. What I'm going to do is I'm going to wrap it up here, and on the next episode where we go into more building science and EPA Moisture Control Guide, we're going to do an odor project, and we're going to do a project in a commercial building which had multiple issues as well. Cliff, any final comments or thoughts?
No, none. Nice job, Joe.
Thank you. I really like the odor thing, Cliff. We're going to talk more about using the 4 Ps in odor investigation. I've got a great one where it was an odd one too, where people were painting in a building, 2-story commercial building. They were doing some painting in that building, and one of the workers, you know, you'd never think this would be a huge issue. He cleaned the brushes outside with a paint thinner of some type, cleaned the brushes, and then dumped the bucket right next to the building. And so one bucket of paint thinner and paint dumped right next to this building caused an odor in their building that led to people having to leave the basement of the building, which is where this office was, had to relocate some people, and had to bring in some professionals, myself included, to help try and figure out why they had this odor and where it was coming from. In that case, it was a lot of detective work by talking to the people who had done the painting, talking to the people in the building, but it was the 4 Ps again, and we'll look at that on the next episode of IAQ Radio. So I want to thank everybody for hanging in there with us today. Next week, we'll be back next Friday at noon. I want to thank our sponsors, of course, my co-host, the Z-Man, Cliff Zlotnick. At the controls, John, you got to have faith. Great job, John. And most importantly, all of you, our loyal listeners out there, downloads are great. YouTube's coming along. People are starting to get used to going to YouTube to check out the shows. We'll be back next Friday at noon for the next episode of IAQ Radio.
For IAQ Radio, I'm Spike Reel saying thanks for listening.